Now that we figured out that in order to solve a second-order linear homogeneous equation, we need to know two linearly independent solutions of that equation. As a first step, let's see if knowing one solution of a second-order linear homogeneous equation would allow us to find the second solution. So let's do an example. Let's suppose that we're given an equation. Given an equation, y double prime plus y equal to 0. Suppose that we know that y1 equal to cosine of x is a solution of this equation. And this we can easily check. So let's check that. So indeed, y1 prime is minus sine x. y1 double prime is going to be minus cosine of x. And then y1 double prime plus y1 is minus cosine x plus cosine x. y1 double prime is minus cosine x. y1 is cosine of x, and that is equal to 0. So it is a solution. All right. We want to find the second solution. A second linearly independent solution. And what I'm going to do is I'm going to look for this solution in the form y2 of x is equal to the function y1 that I know times some unknown function v of x. So v of x times y1 of x, which in this case means v of x times cosine of x. So rather than looking for the function y2, I'm looking for the function v, and I hope that the equation that I will need to solve is going to be simpler somehow. Okay, so then the first thing that we need to do, we need to find an ODE for v. And basically what I'm doing is I'm doing substitution, right? Instead of function y, I'm going to use a function v times cosine of x. So to figure out the ODE for v, I need to express derivatives of y in terms of derivatives of v. So y2 prime is going to be, by the product rule, it is v prime times cosine x plus v times minus sine x. So that is going to be so y2 prime is v prime cosine x minus v sine x. If I want to sub this into my equation, which is y double prime plus y equal to 0, it's not enough to find the first derivative, I need to find the second derivative. So let's look for y2 double prime. What is that? Again, I need to use a product rule, but now twice, both on this product and on that product. So product, the first product, I have to take derivative of v prime, so that should be v double prime times cosine of x plus v prime, first function times derivative of the second function, minus sine x as derivative of cosine. And then I'm going to take derivative of the second product, minus v prime sine x, derivative of the first times the second, minus v times sine derivative of sine cosine x. So if I simplify that, I'm going to get v double prime cosine of x, and I have two terms that look the same, minus v prime minus 2v prime sine x plus v cosine x, and that's my second derivative. So if I want to have y2 solving my ODE, so then since we want y2 double prime plus y to be plus y2, I want that to be 0, then in terms of v, this should be v double prime cosine x minus 2v prime sine x plus v cosine x. Let me make sure this plus is not plus but minus, and this one is minus. So I've just written y double prime, y2 double prime plus y2. y2 is v cosine x, and I want the result to be equal to 0. But now here I have v cosine x, which cancels with minus v cosine x. So then at the end of the day, what we get is v double prime cosine of x minus 2v prime sine x. This would be equal to 0. So what I'm getting is second order ODE for v, right? That is a second order linear homogeneous ODE because I have second derivative of v times function of x plus first derivative of v times some function of x equal to 0. So this is a linear second order homogeneous ODE. And so far, it seems that actually what I did by making this substitution, I made things worse rather than better. Why? Because in the beginning, I had an ODE for y, which looked like this, second order linear homogeneous ODE. And I produced a new second order linear homogeneous ODE, which clearly is more complicated because it now involves jigs. However, as you can see, we'll see in a moment, the main thing about this new equation is that unlike the first equation, it does not have any function, it doesn't have a function v itself. It only has v prime and v double prime, and we'll see in a moment that this actually is going to be helpful. So let's see why it is helpful. What I'm going to do is I'm going to set u to be v prime. If I set u to be v prime, so that is my new unknown function, then u prime is v double prime, right? Because if u is the first derivative of v, then the first derivative of u is the second derivative of v. And so then I'm going to substitute this into the equation. And my equation then becomes u prime cosine of x minus 2u sine x equals 0. And this is actually a much better thing than what I had in the beginning, because now in terms of u, this is a first order equation. It is still linear, but it is a first order equation. So a linear first order ODE, and I can solve it by using the integrating factor. So if I want to use the integrating factor, then we have to write this ODE in a standard form. For that, I'll have to divide everything by cosine of x. So then u prime minus 2 sine x over cosine of x times u must be equal to 0. And so the integrating factor, so then mu of x is going to be e to the power integral of minus 2 sine x over cosine x dx. This looks like a complicated integral, but we can take it by doing u substitution. So if in this case I cannot call this u because I already used the letter u. So let's make it p substitution. Let's suppose that p is cosine of x, then dp is minus sine x dx. And making a substitution, this becomes e to the power, so minus sine x dx is dp. So we get e to the power 2 integral of dp over p. And an integral of 1 over p is natural log of p, so this would be e to the power 2 natural log, in principle, absolute value of p. I want to get rid of e and natural log, so for that we're going to use the properties of log, move 2 inside the log, and we get e to the ln absolute value of p squared, but the absolute value of something squared is exactly the same thing as that something squared. And so p squared is your integrating factor. And of course we have to write p again back in terms of x. P is cosine x, so this is cosine square of x. So going back and multiplying the equation by cosine square of x, we have that integrating factor times u prime now must be equal to 0. So therefore cosine square of x times u prime, this must be equal to 0. And then integrating both sides, cosine square of x times u should be equal to a constant. Now, in this case, I'm going to set a constant equal to 1, because at the end of the day, I'm looking for just one solution, y2 of my ODE, so it would be enough to find only one u, and then only enough to find only one v, etc. All right, so we have this. So we solve for u, and u is 1 over cosine square of x. So set c to 1 then. All right, so if u is 1 over cosine square of x, and I remember what u was. U was v prime. And if u is v prime, so then what we get is that v prime is equal to secant square of x, right? Because 1 over cosine square of x is secant square, and then integrating both sides, I can get v. So v should be an integral of secant square of x dx, and that's a table integral. V is a tangent of x, and I'm not going to write any c's again because I only need one solution. All right, so therefore y2 of x, which is v of x times cosine of x, is tangent of x times cosine of x, and that is sine x over cosine x by definition of tangent times another cosine x. Cosine x goes away, and the second solution is sine x. Now, clearly, sine x is not equal to the constant multiple of cosine of x, so therefore y1 and y2 that we found, they are linearly independent. And we can check this by computing the Wronskian. So that would be cosine x sine x, derivative of cosine is minus sine x, derivative of sine cosine x. Product of the elements on the main diagonal is cosine square, and the second diagonal is minus sine square, so we have cosine square of x minus sine square of x, and that's cosine square plus sine square 1. Wronskian is not equal to 0, so solutions are linearly independent. And so from this we can deduce that sine x and cosine x form a fundamental set right, because there are two linearly independent solutions of our ODE of the equation y double prime plus y equal to 0, and therefore I can construct a general solution of this equation. Y of x is c1 cosine x plus c2 sine x. So what we just did, we reduced the need of finding the two solutions of a second order linear homogeneous equation to the need of knowing just one, because the second one can always be found by using this method that I just illustrated. The method seems to be fairly involved and lengthy, but actually it can be reduced to a single formula. So this method can be reduced to a single formula. Suppose we have an equation of a second order linear homogeneous equation in a normal form. That is, the equation looks like y double prime plus p of x y prime plus q of x y equal to 0. Also suppose that y1 is a solution of this ODE. Then the second linearly independent solution is given by the following equation. y2 is y1 times the integral of e to the power integral of p of x dx divided by y1 square of x dx. So by evaluating these two integrals, you should be able to get the second solution without going through any steps, because this formula that I'm writing is actually equivalent to the procedure that I employed in my previous example. So let's try this formula on the previous example. This is called the formula for the reduction of order. And why is this reduction of order? Remember that substitution that we did in the first example led us to solve a first order equation rather than a second order equation. So we reduced the order. So y double prime plus y is equal to 0, and y1 of x is cosine x. Let's see what we're going to get. I'm just going to use a formula. y2 is y1, which is cosine of x, times the integral. Now, this equation is in the standard form because the coefficient in front of y prime is y double prime is 1. There is no y prime, so that means that the second coefficient is actually 0. So that means that p of x in my formula here is also 0. Notice that the formula does not involve q of x. So this is e to the power integral of 0 dx. y1 is cosine of x, so y1 square is cosine square of x dx. Integral of 0 is 0, e to the 0 is 1, so numerator is 1, so this is cosine of x times the integral of 1 over cosine square of x dx. And then integral of a secant again is tangent, so this would be cosine of x times tangent of x. But we already know that tangent is sine over cosine, so I can simplify the tangent and get sine of x. And so this is my second solution by the method of reduction of order, which I already implemented above, except that now we simply have a formula that we can use. And so then the general solution of the ODE, again, of y double prime plus y equal to 0 is a linear combination of these two solutions that we have. Is C1 sine x plus C2 cosine x. And let me do one more example. Example number 2. Let's suppose we have an equation. Let me see. X squared y double prime minus xy prime plus y equal to 0. Okay. Let's suppose that this equation, or I claim that this equation has a solution. That I can actually see that there's a solution by inspection. Y1 is equal to x. Why is this a solution? Because if I take y1 prime, I'm going to get 1. y1 double prime, derivative of 1 is 0. And then x squared times y1 double prime minus xy1 prime plus y1. That is 0 minus x times 1 plus x, and that certainly is 0, right? So indeed, this guy is a solution, and I want to use reduction of order to find the second solution. And we already said that in order to use this formula, I have to write my equation in standard form. So in this case, it means I have to divide it by x squared. So y double prime minus 1 over x y prime plus 1 over x squared y equal to 0. That's my equation in the standard form. So then the coefficient of y prime is p of x. And then y2 of x should be y1 integral e to the integral p of x dx over y1 squared dx. And now we can substitute what we know into this formula. So y1 is x, right? Times the integral e to the power integral of p. So p is minus 1 over x, so minus integral 1 over x dx. And then y1 is x, so in the denominator I'll have x squared dx. All right. Let me see something here. Okay. All right, so what are we going to get? When you take the inner integral first, e to the power integral of minus integral of 1 over x is minus natural log x. So e to the minus natural log of x divided by x squared dx. This integral looks fairly formidable, but again, the idea is that you should be able to simplify the numerator. So let me do it separately here. E to the minus natural log of x is e to the ln x to the minus 1, because coefficient in front of ln becomes a power of x inside ln. E and ln cancel out, and we get x to the minus 1. And so x to the minus 1, then this is x integral x to the minus 1 over x squared dx. X to the minus 1 also goes downstairs to the denominator, so this is x integral, actually I'm going to write it this way, x to the power minus 1 on the top, x squared on the bottom, so this is overall x to the power minus 3. And x integral of x to the minus 3 is x to the minus 2 over 2, minus 2. Okay, so we can simplify this to get x times minus x to the minus 2, that's minus x over x squared, minus 1 over 2x. So that is my second solution. How would I check if this second solution is independent, linearly independent from the first? Well, in the method of reduction of order, the second solution that I end up with is always going to be linearly independent from the first solution. But in this case, just to check, so check linear independence. And I can do that by computing the Wronskian. So Wronskian of two functions, x minus 1 over 2x is a 2 by 2 determinant, x minus 1 half x to the minus 1. And derivative of x is 1, and derivative of minus 1 half x to the minus 1 is going to be 1 half x to the minus 2. And so what this is then is 1 half x times x to the minus 2 plus 1 half x to the minus 1. X times x to the minus 2 is actually also x to the minus 1. So altogether the Wronskian is x to the minus 1, 1 over x. And we're going to assume here, I'm going to assume that x is always positive. And if x is always positive, then this is never equal to 0. So yes, x and minus 1 over 2x, these are linearly independent. And because this is a second order equation, I got two linearly independent solutions. So the general solution, so x and minus 1 over 2x form a fundamental set. So general solution is going to be y equal to c1x minus or plus c2 times minus 1 half 1 over x. But now I also notice that if I multiply minus 1/2 by C2. C2 is generic constant, so minus 1/2 generic constant is still a generic constant. So I can rewrite this expression as C1x plus C2 over x and forget about minus 1/2. I'll say in this case that minus 1/2, the constant minus 1/2, is absorbed by the generic constant C2. Okay, and in the next lecture now we're going to learn how do we actually solve linear homogeneous equations in a special case when they have constant coefficients.